Okay, so to continue with our quantum numbers, we have the third quantum number, which is your magnetic quantum number. The magnetic quantum number describes the orientation of your subshell of your orbital in space. So how many orbitals are there in your subshell? Within a subshell, the value of your ML depends on the value of your L, which means that ML ranges from negative L, 0, and positive L. So for example, if you have an energy level 1, your L value is 0, so your ML is 0. Obviously, there is no negative and positive 0, so that's only 0. But if your L is 1, so your ML value is negative 1, 0, and positive 1, which means that L corresponds to P. P then has three orientations. That is negative 1, 0, or 1. Or it is depicted as Px, Py, and Pz. If L is 2, which is your D, then it has an orientation of negative 2, negative 1, 0, 1, and 2. So this means that if your S or if your L is S or your S orbital or S subshell, there is only one orientation in your S subshell. In your P subshell, you have three orientations, and in your D subshell, you have five orientations. Next to this is your F, which has seven orientations. Now remember that in the fourth quantum number, you have an electron spin quantum number, which tells you that the spin of the electrons in a certain orbital or a certain subshell is in opposite direction. Meaning to say that for every subshell or for every orbital, for every orientation of your orbital, the maximum number of electrons that it can occupy is 2. For example, here in your S orbital or S subshell, there is only one orientation, and that is 0, which means that a maximum of 2 electrons can be occupied in your S subshell. In your L subshell or in your P subshell, there is a maximum of, or there are three orientations. It means that a maximum of 6 electrons can be occupied in the P orbital. Then in your D subshell, you have 5 orientations, indicating that you have a maximum of 10 electrons occupying the D subshell. So the four quantum numbers of your atom or element will give you an idea to label your electrons in an atom. So for example, if you have a 2s orbital, the quantum number values of your 2s orbital is 2, 0, 0, and 1/2. If there are 2 electrons occupying your 2s orbital, then the other value is positive 1/2. In your 3p orbital, there are 6 quantum number or quantum numbers, or there are 6 ways to write its quantum numbers. So your assignment is to give me the quantum numbers of a 3s orbital and a 2p orbital. So for example, we have here the quantum number of your oxygen. Oxygen has 8 electrons, so we list down here all the 8 electrons of your oxygen. You have your quantum numbers N, L, Ml, and Ms, and the corresponding orbital that it occupies. So the first 2 electrons of your oxygen is found in your first energy level in the subshell S. And in your subshell S, you only have one orientation. 2 electrons can occupy the S subshell maximum. For the next 3, 4, 5, 6, 7, 8 electrons of oxygen, it occupies the second energy level at the S subshell, and the p subshell. At the s subshell again, you only have one orientation and 2 electrons can occupy at a maximum. In the p subshell, you have a maximum of 6 electrons. So since the remaining electrons here is only 4, so it occupies your p subshell with distributed among the 3 orientations. That's the -1 or your px, -0, the py, and the +1. The extra 1 electron or the 8th electron of your oxygen is paired to your one of the orientations. So, assignment again is to give the quantum numbers of your carbon. So, an electron configuration tells you how the electrons are distributed among the various atomic orbitals. But before that, let's have Pauli's exclusion principle first, that according to Pauli, there are no 2 electrons in an atom that can have the same 4 quantum numbers. So for example, in your 2s orbital, s can occupy a maximum of 2 electrons so that the quantum numbers of your 2s is 200 -1/2 and 200 +1/2. So no 2 electrons have the same 4 quantum numbers. And for Hund's rule, the one that I have given earlier about the p subshell or orbital, so the most stable arrangement of your electrons is when it is distributed among the orientations before pairing it off if there is an extra electron. So in the case of oxygen, where we have 4 electrons left in the second energy level, so it will occupy px, py, and pz. If there is one more electron, then you can pair it with the other orientation. So this is an example of the electronic configuration of your element. For example, hydrogen has 1 electron, so obviously it can be found in the first energy level in only the s subshell. And here you have the single electron of hydrogen. In here, in this table or in this illustration, this is an easy way to remember the orbitals that you need to be occupying first. So if you're given an electron or if you're given an element with and finding its electron configuration, so you first occupy 1s. After filling 1s, remember s has a maximum of 2 electrons. So after you fill that, follow it up on 2s. Then on 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. You have to remember that 2p or your p subshell can occupy a maximum of 6 electrons and your d subshell can occupy 10 electrons. The f subshell can occupy 14 electrons. Now in this table here, you can see that helium is found in the noble gas configuration of your periodic table. Now, if you have an element that is found in the noble gas configuration, you can actually make use of helium, put it in a bracket, and continue on with the other elements after helium. So, for example, lithium, the noble gas element preceding or before lithium is helium. So, the electron configuration of your lithium can be written as bracket helium and the remaining electrons of helium, which is 1 or 2s1. Okay, so helium has 3 electrons. Same thing for beryllium, for boron, carbon, nitrogen, oxygen, fluorine. So here in neon, you can also use helium and the remaining electron. But neon is also found in a noble gas configuration. So here, you have boron with 5 electrons. This is one way of writing the electronic configuration, 1s2, 2s2, 2p1. Or the other way is by bracket helium. That's understood to be 1s2 and sorry, here, boron. So that's 1s2, 2s2, and 2p1. Now, for chlorine having 17 electrons, the noble gas element preceding, or that is before chlorine, is neon. So, neon has 10 electrons. So, that's understood if you put in bracket neon, it means it has already 10 electrons. And then the remaining electrons, 7 electrons of your chlorine is found in 3s2 and 3p5.